In the next section, we're going to talk about more graphical displays for data, starting with what's referred to as a bar graph. Well, we've already kind of seen the bar graph in the last section with the histogram, but bar graphs are specifically for qualitative data versus the quantitative data that we use the histograms for. Same idea, the height of the bars represent the frequencies, and technically they could also represent the relative frequencies as well, interchangeably. And to go along with the bar graph is the idea of what they call a Pareto chart. And Pareto chart are where the bars are arranged in frequency order. In other words, you arrange them from biggest to smallest or smallest to largest frequency. Pareto charts really are only making sense when we talk about the nominal data that doesn't already have a inherent ordering to it, like the ordinal data would. In this case, we're ordering it in some fashion here from the frequencies big to small or small to largest. And so let's create a bar graph for this particular set of data here. So we have our layout here of our vertical axis for counting up the frequencies and the number of movies in that category, and then the horizontal axis listing out the different movie rankings. And to create the bar graph here, we'll start with the movie ranking of 1, which only has a frequency of 1. So our bar is going to go up to there. Okay, and then the movie ranking 2 has a total of 3. So we'll make a bar going up to 3. And then for 3, there's a total of 7. So we'll make a bar going up to there. And then for 4, there's a total of 2. So we'll make a bar going up to 2. And then for 5, there's also 2. So we'll make a bar going up to 2. Here's a list of data that we would classify as nominal qualitative data, ice cream flavors, and the number out of 70 shoppers who expressed a preference for each one of these flavors. So this type of data we want to create a Pareto chart for. It's still a bar graph, but it's a bar graph that we're going to order in some way because the data itself doesn't have an inherent ordering to it. So I've set up my axis here so that we have from the most to least in terms of the frequencies in the table. So this one frequency that was the most, the number who preferred it was 35. So we'll draw a bar going up to there. And then the next one had a total of 20 who preferred it. So I'm going to draw a bar going up to there. And the next one was only 10. So let's draw a bar going up to there. And then the lowest one had only at 5. So we'll draw a bar going up to there. And so this is what they again would call a Pareto chart for our data. And then the last type of chart that we're probably familiar with that we'll look at here is called the pie chart. And a pie chart is specifically better for representing the relative frequencies. So that would be the percentages. So the wedges are proportional to the relative frequencies and totaling up to 100% being the entire pie chart circle. So here, going back to some data we had seen, are some of the frequencies of grades along with their relative frequencies. Those relative frequencies are percentages, and that would divide up the pie chart accordingly. So things like 36%, 28%, and so forth. So that's a nice visual representation of relative size within our data set versus sort of an absolute size that we might see in a table, like a bar graph or a thing like that. So here, let's create a pie chart with the data that we have here. First off, I need to calculate the relative frequency so I know the percentages to use. So to do that, we need to first total up all the numbers. So 180 plus 450 plus 270 for a total of 900. And then we take each frequency and divide by 900. So 180 divided by 900 will get 20%, and then 50% and 30%. Here I have the data within Google Sheets if you want to create a pie chart using a spreadsheet program like this one, let's go ahead and have our data, and then I'm going to click on Insert Chart. And in this case, it's smart enough to know that we wanted to create a pie graph. And that's pretty much all we have to do here. We could give it a title. And again, if you ever want to change the type of graph, if you're using different things, you can go over here to Setup and then Chart Type, and there's a whole lot. We could even change it to a bar graph if we want to. And you can see how the bar graph shows the absolute frequency numbers versus the percentages that we saw in the pie chart. In this example, it gives us a pie chart, and this pie chart represents the percentages spent on outdoor activities such as fishing, camping, hunting, and golf. The total amount was 9.3 billion according to this survey, but using these percentages, how much was that of that 9.3 billion was spent on camping? So looking at the pie chart here, we can tell that camping had a percentage of 18.28%, which is as a decimal equal to 0.1828. All we have to do is to multiply the total 9.3 for 9.3 billion by the decimal 0.1828, which gives us approximately 1.7, telling us that approximately 1.7 billion from this pie chart in total would have been spent on camping. Then another thing that they often refer to is called a stem plot or a stem and leaf plot. And it's somewhat like a histogram, but instead of bars, we're actually going to see a listing of the numbers that are in the data set. So let me create a histogram and a stem plot for the data below. In a stem plot, we're going to have basically a column for each digit in our number. So we'll start off with like the tens position and the ones position in each of the digits that we have above. And so we'll list out the numbers that have tens. So like we have a number in the 40s, 5, 6, 7, 8, and 9. So that would be 40s, 50s, 60s, 70s, 80s, and 90s. And then next to that, we're going to list out the digits in the ones position for each of the numbers. So we have a 42, and so for the ones digit, I'm going to put a 2. Notice that there are no numbers in the 50s, so we're just going to leave that empty. For 60s, we have a 67, so I'm going to put a 7 there. And so far we've only had like a one number that were like in the 40s or the 60s. So if we look at the next one though, in the 70s, there's actually two numbers that have a 7 in the tens position. A 73, so we'll put a 3 there for that ones position, and then an 8 for the other number that's in the 70s. And then for 80s, we have 82, 84, and 86. And then for 90s, we have a 91, 94, and 99. And so this is how we construct a stem and leaf plot or a stem plot for a particular data set. The idea is it shows you the distribution of the data. So we can see how a lot of the numbers are tending toward the 70s, 80s, and 90s, and there are fewer numbers in the lower end of things. So again, it is a visual representation of the data, but it's interesting that it also includes the numbers themselves at the same time. Let's look at another example which gives us a stem plot, and we're going to answer some questions based off of this. These are fuel efficiency ratings in miles per gallon. So the first question is, what are the MPG ratings for cars in the 40 MPG range? So that would be the numbers that have 4 in the tens position. So we would notice that there are two values listed in the 40s, 40 and 47. So 40 and 47 are the two numbers listed here with the 40 MPG, in the 40 MPG range. The next question is, what's the highest MPG in the 30s? If we look at the numbers in the 30s, have 3 in the tens position, and then the largest number in the ones position is the 8. So 38 would be the largest value in the 30s according to this stem plot. And then how many cars have MPGs in the 20s? So miles per gallon in the 20s, we look at the numbers that have 2 in the tens position, and then we have a 0, 7, and 7. So that refers to a 20, a 27, and a 27. So that would be 3 values within the range of 20s. Something to talk a little bit about before we end off our discussion on graphs and charts is looking out for graphs and charts which may be deceptive. Here is a picture that may be deceptive. It's meant to show the relative value of a dollar in 1980 and 2015. And so it makes sense that the smaller graph, the smaller representation would be less valuable, in this case only 35 cents. The issue with this particular picture is the width and the length are shrunk by roughly a third to represent that the dollar's, in that case, about a third of what it used to be worth. But by doing so, it actually shrinks the area by more than that. It's actually only 12% of the area of the original dollar bill in the picture. So that causes a visual representation that might give people the wrong idea, making it look smaller than the actual value is actually shrunk by. So that's a possible place to look for. In pictographs such as this one that visually represented in a picture, look for the relative sizes and see if they're not exaggerated in some fashion. I have a kind of an exaggerated example of this in this next picture here. This is a real graph that I found somewhere. It's meant to show the average height per country. And they're trying to use a bar graph here, but it doesn't really come off very good. So you can probably tell something's not right here in terms of the relative sizes in the graph. This is a graph that doesn't do such a good job if you want to use it to kind of represent the sizes in a manner that would be appropriate in the real world. So watching the scales is a very important thing to do. So these two particular graphs says women as a percentage of all college students. So we get an idea of what's going on here by looking at the graph, but if we try to actually read it, how much does the actual percentage of women college students vary? In 1950, it shows the lowest is 30%, and for 2010 and beyond, it's closer to like the high 50% range. It doesn't ever get up close all the way to 60 from the looks of things. But because the left graph does not start from 0, this difference is exaggerated visually a lot more than it would be otherwise. So look for graphs that might have the scale starting from something other than 0. Those might give you an exaggerated visual sense of how much the data changes. Here's another real-world example of this. And can you see what might cause some misunderstandings or misinterpretations from how this graph was designed? There's a few issues. One of them is along the horizontal scale. Notice that from left to right, it goes from 2021 to 2018. So the labels along the horizontal axis are more or less reversed to what we would normally think, going backwards in years rather than forwards. Also, just like that last one, the vertical scale does not start from 0. So since it doesn't start from 0, the ups and downs seem more exaggerated than they would otherwise. Here's another watch the scales situation that you might watch out for. These are the same data numbers, but they've been represented in two very different ways. One is what we would call a exponential scale in powers of 10, and the other would be called a what they say linear scale, which is increasing by like 10,000 or 20,000 each time. And so looking at the numbers along the vertical axis is very important because they reveal, like genuinely what the numbers are supposed to be rather than the visual sense that we also get along with our graph. Here's another one to look out for. This is a line graph and a bar graph kind of put side by side. One says changes in college costs. The other one says actual college costs. The big difference here is The one on the left shows you percentages, while the one on the right shows the actual amounts along the vertical axis. So looking at the percentages, you can see how the percentage change has been greater or less in certain years, but at no year has the percent of change gone negative. So in other words, the costs have always increased according to that. It's just been more increase or less increase in certain different years. And you can see that in the bar graph, how the bars are always going up. They're just not going up by as much in some years as the other. So two different ways of representing the data, either as a percent change or the actual absolute value. It can give you a different sense of how things are changing, but you have to look at the scales to make sure that you are reading off the numbers that they're giving you correctly.